So let us find Taylor series expansion of a function. Actually, right now what I'm going to find is called Maclaurin series. I'll tell you the difference between Taylor's and Maclaurin's. So f of x equals to e power x I am taking. So here to find Taylor series expansion, we need to know all these things. That is f dash of 0 and all, right? So first let me find f dash of x here, which is e power x only, and this would be equal to second derivative, and even this is same as the third derivative, and so on. So all derivatives will be equal to e power x only. Therefore, here we can see that f of 0 is 1, and f dash of 0, that is e power 0, that also becomes 1. F second derivative at 0, even third derivative at 0, and all these derivatives would be equal to 1 only. Okay, so now let us write the formula for Taylor series expansion. What is the formula? So the Taylor series expansion, f of x equal to, so what will it be, sir? So f of 0 plus f dash of 0 into x plus second derivative at 0 by 2 factorial into x square plus third derivative at 0 by 3 factorial into x cube plus and so on. So if I substitute the values here, so the first one, you know, that is 1 plus next is also 1, therefore it is x, and next it is 1, so x square by 2 factorial plus next will be x cube by 3 factorial, and of course next one also you can write x power 4 by 4 factorial plus and so on. Okay, so therefore we can conclude that the Taylor series expansion of e power x is going to be this. In other words, we can say that e power x is equal to summation n equal to 0 to infinite x power n over n factorial. Okay, so we got Taylor series expansion of e power x. Okay, so for any function, this is what you need to do. First you list out the derivatives and find the derivatives at zeros and simply substitute everything in this formula. That's it. So let's take one more problem. Maybe let's take f of x is equal to cos x. So what is the Taylor series expansion of cos x? So the same thing we will do now. So first we will write f of x. F of x is cos x only, and next you may look at its derivative. What is the derivative of cos x? That is negative sin x. And the second derivative of x is minus of cos x. Okay, but it's not like the earlier one. The earlier it is exponential, therefore derivative is e power x only. But since it is cos x, it oscillates between the cos and sin, right? So third derivative is going to be minus into minus, we'll get plus sin x. Yeah, and the fourth derivative at x, that will be cos x. Okay, yeah, I hope these are enough to guess. Now from this you do one thing, you find f of 0. What is f of 0? F of 0 is cos 0, and that equals 1. And what is f dash of 0? F dash of 0 is minus sin 0, but you know sin 0 is anyway 0. And next, second derivative at 0, that is that is minus cos of 0, so which is -1, and third derivative at 0, which is sine of 0, which is 0, and even fourth derivative at 0, that is cos of 0, which is 1. But we can observe the pattern. Like first we have one, every odd derivative is becoming 0. That's what we can observe. And after that, the second derivative become -1, fourth derivative is positive. Again, sixth derivative will be negative. Then eighth derivative will be positive. So that is how it is going to come. Okay. So let's write the Taylor series expansion. The Taylor series expansion, which is f of x equals to, so that is f of 0 plus f dash of 0 into x plus second derivative at 0 by 2 factorial into x square plus third derivative at 0 by 3 factorial into x cube plus and so on. Okay, so we substitute it. F of 0, it means what is f of 0 here? 1. That is 1. Okay. Plus, and next one is 0 into x. Plus, next one is the second derivative, that's -1. So -1 by 2 factorial into x square plus 0 into x cube plus, and that is 1 over 4 factorial into x power 4 plus 0 into x power 5, and next one would be -1 into x power 6 by 6 factorial plus and so on. Okay, this is going to be 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus and so on. So this is the expansion of cos x. In other words, we can of course write the nth term for it. So therefore, the expansion of cos x, that's going to be summation n equal to 0 to infinite minus 1 to the power of n into x to the power of 2n over 2n factorial. Okay, so this is the expansion of cos x, and you know this expansion is going to be valid for all x belongs to R. Valid, it means that this expansion is convergent to cos x for all values of x. That is what we mean by valid. Okay, so this is how we find Taylor series expansion for cos x. Only thing, you need to just list out the derivatives and find the derivative values at zeros and finally write it. Now let's do one more thing. Now this time I want to have expansion of the same function but not above 0. Okay, ఇక్కడ మనం యాక్చువల్గా ఏం చేస్తున్నాం, 0 దగ్గర డెరివేటివ్స్ ఫైండ్ అవుట్ చేసి ఈ ఎక్స్పాన్షన్ ఫైండ్ అవుట్ చేస్తాం. బట్ ఇక్కడ 0 దగ్గర కాకుండా వేరే పాయింట్ దగ్గర కావాలి. ఎగ్జాంపుల్ 5, I want, or 5/2, I want the expansion at 5/2. So how to get it? So in that case, so మన function f of x ni, instead of writing a0 plus a1 into x plus a2 into x square, we can actually write it like this: a0 plus a1 into x minus c, where c is the point that you want. Okay, c అనేది a అని రాస్తుంది. Okay, plus a1 into, sorry, a2 into x minus a whole square plus a3 into x minus a whole cube plus and so on. So it means you are writing an expansion centered at a. So if you write an expansion centered at a, then you need to find these values, right? What is a naught? I hope you can easily see that a naught is nothing but f of a, because when you plug in x equal to a, you'll get a naught. And how about a1? Like earlier, we need to differentiate, and you plug in, just differentiate and plug in a. That's it. Okay, so this gives you a1, and similarly you can get a2. So a2 can be obtained by second differentiation and plug in a, and of course here you'll get 2a2, therefore 2 will come to the denominator. And now you can write a3. a3 is going to be third derivative at a by 3 factorial. So a4 is going to be fourth derivative at a by 4 factorial. Okay, so these are the coefficients in the Taylor series expansion. So finally, the expansion f of x is going to be summation n equal to 0 to infinite. So this is nth derivative at a by n factorial into x minus a whole power n. Okay, so this is what we call Taylor series expansion centered at a. And if you have a Taylor series expansion centered at 0, that is called Maclaurin series expansion. So Maclaurin series expansion, it means if you plug in a equal to 0, that is Maclaurin series expansion. So whatever we have found earlier, for example, this one cos x at 0 and similarly this e power x expansion at 0, these are called Maclaurin series expansions. Okay. And that is also called Taylor series expansion. Maclaurin series is also a type of Taylor series expansion. It's a specific case in the Taylor series expansion. That's it. Maclaurin's first found that 0 thing, and Taylor's extended this to non-zero things like this. So that is the thing. Right. So let's do one thing now. Now let me take some function f of x equal to root x. Is root x better? No. Let me take cos x only. Let me take sin x this time. F of x is equal to sin x I am taking. Now you need to find expansion of sin x. Find Taylor series expansion about x equal to pi. So about x equal to pi, we need Taylor series expansion of sin x. So it means what we have to do. So we need to find first we list out these things. F of x, that is sin x, and f dash of x, what is it? Cos x, and the second derivative is minus sin x, and the third derivative is plus cos x, and the fourth derivative is minus sin x. Oh, why do I write plus cos x? This is minus sin x, minus 1, no? Yeah. And now this becomes plus. Okay, and we can keep on write like that. And okay, now let me find f of pi. So f of pi is nothing but sin pi, but you know sin pi is 0. Okay, so f dash of pi, what's it? That is cos pi cos pi is -1, and second derivative at pi, that is sin pi minus sin pi, that is 0. Third derivative at pi, that is minus cos pi, which would be minus of minus, that becomes plus 1. Okay, and similarly we can think about the other derivatives also. And if you want one more also we can write. Fifth derivative we didn't find, but still we can write. It's going to be -1. Yeah. Okay. So now let's write Taylor series expansion formula. So f of x equals. We need expansion centered at pi. Okay. So that is f of pi plus f dash of pi into x minus pi. This is important. X minus pi plus second derivative at pi divided by 2 factorial into x minus pi whole square plus third derivative at pi over 3 factorial into x minus pi whole cube plus and so on. Now we may substitute one by one. I hope f of pi is 0 and the next one is minus 1. So minus 1 into x minus pi plus next one is 0 plus and the next one is 1. So 1 over 3 factorial into x minus pi whole cube, and next one anyway becomes 0, and next one you get minus 1. So minus 1 by pi factorial into x minus pi plus and so on. Okay, so let's write it. So minus of x minus pi plus 1 by 3 factorial into so x minus pi whole cube by 3 factorial minus x minus pi whole power pi by 5 factorial plus x minus pi whole power 7 by 7 factorial minus x minus pi whole power 9 by 9 factorial plus and so on. And we can also write its nth term. What is the nth term? Therefore, this is the expansion of sin x about pi. Okay, as a final conclusion, let's write this. Therefore, sin x equals summation n equal to 0 to infinite minus 1 to the power of n. I'd like to do one thing. Instead of starting with 0, I'd like to start with 1. Okay, and so this would be x minus pi, and this would be 2n minus 1 over 2n minus 1 factorial. Okay, and this is the expansion of sin x about pi, and this is also going to be valid for all x belongs to R. Okay, so we can write series expansion of the function at any point, provided that function is differentiable at that point. That's it. Okay, so similarly you can find sin x expansion at 0, at pi by 2, at different points also. Okay, so now I'll give you a simple question here. Suppose if I take f of x is equal to root x. Okay, now I want Taylor's quadratic approximation of it. Quadratic approximation or quadratic polynomial. at x is equal to 1. So can you guess what we need to do here? Taylor's quadratic polynomial, it means they don't want the entire expansion, just up to quadratic term the expansion is enough. For example, okay, I'll do this C. So here f of x equal to, okay, since they said Taylor's quadratic polynomial, let's name it as T2. So therefore T2 of x is equal to f of 1 plus f dash of 1 into x minus 1 plus second derivative at 1 by 2 factorial into x minus 1 whole square. So this equals to what? I hope we need to find f of x and f dash of x. F of x is there. So f dash of x is nothing but 1 by 2 root x. And the second derivative we need to find. The second derivative is going to be 1 by 2, you'll have it like that, and you'll get minus 1 by 2 and x to the power of minus 3 by 2. Okay, so I hope you can see the function value at 1. So f of 1 is 1 only, plus f dash of 1 is 1 by 2 into x minus 1, plus and f second derivative at 1, that is minus 1 by 4. So minus 1 by 4 by 2 factorial into x minus 1 whole square. So that is 1 minus of x minus 1 by 2 plus minus 1 by 8 into x minus 1 whole square. Yes, sir. మీరు ఇంకా సింప్లిఫై చేస్తా అంటే చేయొచ్చు, but anyway. Okay, so now I can ask something like this. Yeah. I may ask you to approximate f of 1.1 value. What is f of 1.1 value using this approximation? So in that case, what we can do is f of 1.1 can be written as T2 of 1.1 using approximation. Okay, so that equals 1 minus 1.1 by 2 plus, sorry, minus in the class with plus 2. Okay, and this is plus minus 1 by 8 into 1. Oh shit, this is 1.1 minus 1. Okay, so this is also 1.1 minus 1 whole square. So now just you need to find this value, right? 1 plus 0.1 by 2 minus 0.1 whole square by 8. So we'll get square root of 1.1 value approximately without using calculator. Yeah. So basically, geometrically, what happens is, generally if you take some function, okay, assume that the graph is like this. So at some point you are making Taylor series expansion. For example, let me take a graph like this. For example, if you are making Taylor series expansion at this point, for example, if it is of only first degree, it will be a line like this. Okay, it may agree at just at one point, and if it is quadratic, it's a kind of like this. Okay, and of course I can go with Desmos. Just a minute. So here, what I can do is, I'll take this function, for example, cos x only, because we already found the expansion. No? So this is a function cos x. So if I take here, the first degree is just 1. Yeah, because 1 plus 0 into x we got. So you don't get anything there. So I need to write it like y equal to, yeah. Now you see, it's just a line. Next, if I extend it, it's like 1 plus x squared by 2. Yeah. So 1 plus x squared by 2 I have to take. By 2. Yeah. Okay. You see that if you observe the line and the parabola, it is agreeing near 0 only. But if you move away from 0, the difference between the approximation and the exact value is too much different. Okay. So next, let me do one thing. Let me take the next level approximation. I hope it should be 1 minus, not 1 plus. Yeah. Okay, now this is 1 minus x squared plus x to the power of 4, x to the power of 4 divided by 4 factorial. Now you see, the initial one is line and the next one is parabola, which somewhat agrees up to some extent. And next one is 4th degree, and that's little better compared to second degree. Now similarly, if I go for one more term, minus x to the power of 6 divided by 6 factorial. Yeah. You see it now? Okay, so as degree becomes higher and higher, then what happens is it almost agrees with the function. So this is how it looks like. Okay, but here if you observe that, suppose even if you stop with the 8th degree, it means here, up to here you are coming, right? So you can maintain minimum amount of error from 0 till what point, I hope. So here I hope till -4. Maybe up to -4 you can have minimum amount of error. Okay, and similarly up to +4, between -4 and +4. But if you go beyond +4, okay, so here you see the approximation is going this direction and the function is moving in this direction. And take it and cos x value find out just after the cos 6 value ఎటువైపు ఉంటుంది. Okay. Next, అదే approximation లో 6 చూస్తే ఎక్కడ ఉంది, ఎక్కడో ఉంది. I think it is somewhere 14, I think so. సో ఇప్పుడు మనం 0 దగ్గర అప్రాక్సిమేట్ చేసినప్పుడు మీరు 0కి దగ్గరలో ఉన్న వాల్యూస్ కి ఆ అప్రాక్సిమేషన్ తో ఫైండ్ అవుట్ చేస్తే అప్పుడు మీకు ఎర్రర్ తక్కువ వచ్చి వస్తుంది. ఓకే, అదే మీరు 0 దగ్గర అప్రాక్సిమేట్ చేసి 100 దగ్గర వాల్యూ అడిగారు అనుకోండి, దెన్ యూ విల్ గెట్ లాట్ ఆఫ్ ఎర్రర్. అంటే యాక్చువల్ వాల్యూ 1 అయితే అక్కడ వచ్చిన వాల్యూ 100 200 అయింది. ఓకే, సో ఎగ్జాంపుల్ కి ఇందాక రూట్ ఎక్స్ ఇచ్చి 1.1 వాల్యూ అడిగా, అది ఫైన్. ఒకవేళ నేను సేమ్ రూట్ ఎక్స్ ఇచ్చాను, బట్ దిస్ టైమ్ ఐ వాంట్ ద వాల్యూ ఆఫ్ 4.1. So if you want the value of 4.1, what will you do? We will approximate, or we will write Taylor series expansion at x is equal to 4. Okay, you write it at x equal to 4, and then you try to find the 4.1 value, square root of 4.1 value using that approximation. Okay, but I hope here you are clear how to find Taylor series expansion of the given function. So the main aim is this one only, finding Taylor series expansion of the function. Yeah, so any questions or doubts?